Okay, hello everyone. Welcome to today's lecture. So last time we were talking about timers and counters, and we first wanted to clarify what is the difference between a timer and a counter. And after that, we started talking about different registers associated with timer counters in AVR microcontroller at Mega 328P. Okay, so the registers which we mentioned, they were the timer counter register 0, which is actually used to hold the initialized value, which is incremented on every clock. Other than that, we have control registers, two control registers per timer or a counter. And also we have two output comparison registers for each timer or counter, which are named as OCR0 for timer 0, but there are two versions or two copies of the same output counter register, and they are named as OCR0 A and B, right? So last time we stopped where we were talking about at the point where we were talking about an example to write a program uh, that waits 15 machine cycle to toggle the output pin PB5 in normal mode. And by normal mode, remember we said that our timer, it can operate in four different modes: normal mode, CTC mode, PWM mode, and the stopwatch mode, right? So we are going to cover, as I mentioned last time, only normal mode and the CTC mode. So in normal mode, what happens is like the value with which you initialize the counter, and once after initializing, once you enable the timer, so the value of the register, it increases on every clock cycle until it reaches the maximum value. So if it is an 8-bit register, the maximum value is FF, and then at FF it changes to 00, where the overflow happens, right? So what does it mean? It means like if our timer is operating in normal mode and we want to uh, write a program which generates a delay of 15 machine cycles. So we need to know what value to put in the counter register, right? So remember we said last time that we can actually use this flag output, or the flag register, sorry, the flag indicating that there is an overflow, to find whether the register has reached its maximum value or not, right? So what is the maximum value? Maximum value of an 8-bit register is 50 is FF, right? So when will overflow happen? When this value will change from maximum to minimum, which is 0. So at this time point, so it will take one clock cycle for this value to be changed from FF to 00. So it's mean that if this is one clock is covered here, right? So how many clocks we need, how many additional clocks we need, right? So here, remember we said 15 machine cycles. So one machine cycle is one clock, right? So it's mean we need 14 other than 14 more, right? So if we initialize the register value which such that it is 14 less than the maximum, so we will get what? We will get the a delay of 15 machine cycles, right? And the easiest way to do is like you can find the maximum number of values, not the maximum value. The maximum number of values which can be stored in a register, which is 256. The maximum value is 255, but maximum number of values which can be stored, total number of values which can be stored is 256. So you can simply reduce, subtract your desired number of machine cycles from total number of values. So like you can do 256 minus 15, and you will get, I guess I remember from last time it was 241. So you can simply put the 241 in the register to generate a delay of 15 machine cycles, right? Here they have done this example in using the hex code. So 15 is equal to 0f, and 256 is 100 in hexadecimal. So when you subtract, you will get the value of f1, right? Which will I expect is equal to 241. So you need to initialize this register with 241 or 0xf1. Okay, so yeah, let me simply uh, erase these annotations. Okay, so the other thing is, that so we need to know we need to use two things. One, well, we need to know what value we need to upload. Need to know sorry, we need to know the value with which we would initialize the register. And the second thing is that we want to use our timer in the normal mode. So, but we also need to select the frequency, right? The clock frequency for the register or the timer. So internally, your clock of this register is connected with the output of this mux here, right? And this mux has different inputs from like which are shown here on this diagram, right? So 8 different inputs. So and it has 3 control signals or select signals. So depending upon these values of the control signals, one of the 8 inputs will be connected with the output. So what we want to do in this example is that we want to use for the clock for the timer the same clock frequency as operated which our whole microcontroller chip is operating, right? So what we will do is that we will simply set the value of these 3 select signals equal to 0, right? And how we will set not equal to 0, equal to 1, right here. So how we can set it equal to 1 by writing in these 3 bits of the least significant 3 bits of the control register B, the value of 001. And how we can select the normal mode operation by setting, let me just use a different color, by selecting all setting all bits equal to 0, WGM02 down to WGM00, right? So two of these bits belong to the control register A and one bit belongs to the control register B. So actually we need to write these two control registers to configure our timer, the mode, and to select its input clock frequency, right? So before writing the actual code, let's have a look at like pseudocode written in like plain English language. We are not using any symbols here. So first we need to give an outline of we want to give an outline of the code. So here is the outline. We first need to initialize the port B pin 5 for the output. Why? Because we want to toggle this output, right? So when we say toggle, so we want it to be like what we wanted to show is like is its values, we want it to be like this. So we want its value to be 1, right, for 15 machine cycles, and then 0 for next 15 machine cycles, and then again 1 for 15 machine cycles, and then again 0, and so on in a continuous fashion. So for like it is running in an infinite loop, right? The other thing we need to do is that we need to write the correct values in the control register A and B of the timer 0, right? So that we can operate the timer in the normal mode with the clock source having the same frequency as the as our AVR microcontroller. The other thing is that the next thing is that we need to also initialize the register of the timer to the correct value, which in our case is F1, right? So what we will do is that we will initialize the register with F1, and then we will first output a value of 1 on the PB5, right? And then initialize the register with the F1, and then wait for the flag overflow flag to become 1, right? So when and we will just be we continuously keep monitoring the flag, and once the flag becomes equal to 1, it will tell us that okay, now 15 cycles have passed. So what we will do is that we will toggle the value on the PB5 pin, and then we will again put the value of initial value of this F1 in that register, and again we will start monitoring the overflow flag, and we'll keep doing this in infinite loop. Okay, so the next step is, so the next thing we need to do is like we need to loop to check for overflow flag of the timer 0 in the TIF0 timer interrupt flag register 0. Remember, we talked about timer overflow flag in the last lecture. So we just need to continuously monitor it after putting the initial value of 1 in the register, timer register, and starting it, right? So when we find it that okay, this the overflow happens, then we need to stop the timer, right? And clear the overflow bit in the TI for 0 register. because why we want to clear it, because we want to monitor it again for the next overflow, and we want to detect the next overflow. How it is possible? First we have to clear it, otherwise if we don't clear it, it will always remain one, right? And then after clearing it, we will toggle the bit of 5 of the port B. So initially we wrote 1 here, then now we will write 0, right? And then we will go back to step 2. uh, not step 2, but uh, yeah, actually we need to go back to step 2, because when you select the clock frequency, at that time your timer starts incrementing the value. Here, remember, in the step 5, we are stopping the timer, and when we say stop the timer, basically what we are doing is that we will select this as an input. So when you select this input, input of the max, it means that you are not providing any clock, so there is no transition, so your counter will not be working. It will not be incrementing any value. It will hold whatever it has. Okay, so there is an important point that you need to consider. Remember, in step 6, we said that we need to clear the overflow bit of the timer, right? But it is important to note that in order to clear, you must write 1 to the overflow bit in TIFR register. So again, you need to write 1. Writing 1 will actually, when you will write 1, hardware will reset it equal to 0. If you try to write 0 to it, it will not be reset. It will retain its value. Okay. So that is important. It is like kind of counterintuitive, but this is how it works. You need to write 1 to that flag in order to clear the flag. Any questions? Okay, so then let's go to the poll. Uh, week 11, day 1, quiz 3. Yeah, okay. Go ahead, select, do this one, and you have 60 seconds. Okay, I ended the poll, but let's have a look at the correct answers. So timer overflow 0 is set to 1 when uh, your TCNT values TCNT 0 value changes from FF to 00, right? And which is like from maximum value, it changes from maximum to minimum. Uh, then second question, timer overflow 0 is set cleared or is cleared by programmer by writing what value to it? 0 or 1? 1. You need to write 1 to it to clear it. Okay. Uh, so now let's have a look at the actual program. We have seen what value we first calculated, what value we need to put in the register. It was F1 in hex form, and the other thing we also figured out what values we need to write in the control register, right? So first we are simply initializing. We're using the directive to set TOV0 equal to 0, right? Uh, and then we are loading 0x20 into R16. Why? Uh, it will become clear. I don't remember, but let's continue, and then it will become clear why we are putting 0x20 in R16. Okay. So then we first need to configure the PB5 as an output. So we are loading 5 in DDRB. So and then not we are not loading. We are actually using SBI instruction, which will set the bit 5 of the DDRB register. So PB5 will then be configured as an output pin. And then we are loading 0 in R17 and outputting uh, and writing R17 on the port B. So which will basically mean that now your PB5 is set equal to, so let me just try it here. So, so initially it is set at 0 here, right? The PB5 is, so if this is 0 and this is 5, so initially now PB5 is set equal to 0 here, right? So, and then we are loading in R20 the initial value which we want to put in the register, the TCNT0 register, but we cannot write it directly. So we first putting it in R20. We are putting it 0xF1 in R20. You can put this, either you can use this equation and then your assembler will do the subtraction or math for you, or you can do it on the paper and then put the value of 0xF1 here. So, I would always prefer to use this decimal form because it is easier. I can simply write here LDI R20 gamma 256 minus 15. So then I don't need to worry about the hexadecimal form, right? It is easy for me to understand. And then we are since these all these registers associated with the timer, they are in the standard IO address space. We can use the IO instructions with them, like in, out, or SBI, or CBI, and so on, or skip if the IO bit is set or cleared, right? So here we are simply using the out instruction to write the value of R20 in the TCNT0. Now TCNT0 is initialized to 256 minus 15, whatever it is. Okay. Uh, Now, after that, we need to put the values in the control registers. So remember what value we had to put in the control register A. For that, we can go back to the figure with the previous slide. So we need to put all zeros in the control register A, and we need to put the value of 1 in the control register B, right? So here we are putting 0 in R20, and then we are using the out instruction to put the value of R20 into the control register A, right? And then we are putting the value of 1 in the R20 and then writing that value to the control register B. Now, what we need to do is, according to if you follow this like these steps which we need to we need to write for which we need to follow in order to write a program. So after like putting the values in the register, we need to now monitor the flag, overflow flag, right? So remember in the okay, let me go back to that register slide again. So here when in register B, when you write the value like 001, so now what you have selected, this line here, this source has an input clock, right? So now your timer will start working, or it will start incrementing with the value which you have initially placed in the register, right? So after that, what you need to do is like you need to monitor the flag, right? So for monitoring the flag, what we can do is actually we can use this instruction skip if the IO bit is set, right? Remember we said that all the registers associated with the timer or counter, they are in our standard IO address space. So we can use this instruction SBIS. So here what we are saying is we are saying like uh, skip the next instruction, or jump again, skip this instruction if the bit 0, remember TOV0 is defined equal to 0, right? So if the bit 0 in this register, TI for 0 is set, which is the overflow flag bit, right? So if it is set, then we will skip the next instruction. Otherwise, the next instruction will not be skipped. So if it is not set, then this instruction will not be skipped, and we will like continuously we will be executing this instruction, or we will be monitoring the flag. And once the flag is set, the control will fall through to the next instruction. Then in the next instruction, what we need to do, remember, next thing we need to do is is to stop the timer. And how we stop the timer? If we go back, we started the timer by writing here the value of 001. And how we can stop the timer? If we select this input, which is actually no clock, right? So we need to write here 0. So what I can do is that instead of writing the whole register, I can simply say clear the 0th bit of the control register B, right? And this is what we are doing here. So simply we are saying that clear the 0th bit of the control register B. Now your timer will be stopped. And then you also need to clear the flag. And remember how we clear the flag? By writing 1 to it. So if I say, yeah, there is a mistake. I should fix it. Let me fix this right now. Instead of saying CBI, I need to say set the IO bit, right? Because setting will actually clear it. So here I'm saying set the 0th bit of the TIFR0 register, so which will actually clear the flag. And after that, what I need to do is, remember, we need to generate an output which is toggled after every 15 cycles. So initially it was set equal to 0, then we waited for 15 cycles when the overflow happened, and when after at that point we stopped the timer, we cleared the flag, and now we need to toggle the output, right? So how we can toggle the output? In R16, we had the value of 0x200, right? So it is equal to 0, 0, 1, 0, 0, 0, 0, and 0, right? And we are uh, doing exclusive OR with R17, which is R0. So when you will do the exclusive OR, initially we wrote R17 on the output. So we had 0 here on the output pin PB5. Now when you will do the exclusive OR with R0, so here you will get 1, and in R17, so the new value of the R17 will be 0x20, and now you are saying, okay, write R17 to the port B, so the output you will have 1. Now in the next iteration, what will happen? You will again do the exclusive OR with R16, and when you will do the exclusive OR, so here it will be 1 and 1, and the output will be 0. So then you will write R17 on the output, and it will become 0, and so on. Next time it will become 1, and so on. It will continue in that fashion, right? Any questions? And at the end, we are simply jumping back to the label to make it an infinite loop. Okay, here is the like C equivalent version of the same program, only to like help you understand the logic at a more human readable level. So here what you have is like you are first configuring the pin B5 as output by writing first you shift 1 5 times to the left, and then put that as a value in the DDR-B5, so which is effectively setting the PB5 in configure in output mode. It is configuring it in the output mode. And then you are writing on port B the value of 0, right? So here you are saying uh, shift 1 to the left 5 times, so the bit at the position 5 will be 1. Then you are saying, okay, take the complement. So when you will take the complement, it will be inverted, so the bit in position 5 will become 0. And then you are saying and it with whatever current value you have in the port B. So irrespective of what value you have in the current B, since the bit in fifth position is 0, so the port B will have its fifth bit set equal to 0, so which is actually output bit. So on the output you will have initially 0, right? And then you are entering an infinite loop. You are putting the initial value in the register, and then you are putting the value in the two control registers A and B, which we have already seen. And then you ask, okay, continuously you are monitoring the value of the overflow flag, right? And so what you are doing is here basically you are saying, okay, shift one, 0 time to the left, and then end it with the value of the uh, TIFR0 register, right? So if the zero bit at the zeroth position in the TIFR0 register is zero, then the output will be equal to zero, right? So, and you will stuck in this loop as long as your flag is not set. So when the flag is set, so this condition will become false because the result will be not equal to zero as a result of this AND operation. And then here what you are doing is you are simply stopping the timer by putting zero in the control register B. And here you are writing one into the TFR0 in the bit position one of the TFR0 register. So you are actually clearing the flag, and here you are toggling the value of the port B. So this time now it will become one here. Okay. Any questions? Okay. Before we okay, before I go to this question, actually I just want to clarify something. Remember in one of the previous slides or in the previous lecture, we talked about low and high directives, right? And for example, let's say if I have load immediate R16 low 0x F024. So we said that what it will do is basically it will put in R16 the value of 0x24. And the other thing is like uh, we also use the high directive, right? And we said that what it will do is that it will put in R16 the value of 0x F0. So the thing is like I was reading the book, and in the book they have used these directives low and high. So actually the directives, they are not the part of the assembly language, but they are the only instruction for the assembler. Now it depends, all depends on what assembler you are using. The assembler used in the book is Atmel Studio assembler. So it is also an assembler for the ATmega328P microcontroller. So in that assembler, Atmel Studio assembler, they are using these keywords for low and high directive. However, if you use this low and high, these like versions of low and high directive in your Arduino IDE, you will get an error. So in Arduino, they don't spell it like this. So what they do is like they use low 8 and 0xF024. So in Arduino, this will be the right way to do the things. So in Arduino, if you use low LOW and high HIGH, you will get an error. Okay, so you need to use LO8, low 8 and HI8, high 8 for low and high. Okay, so I just wanted to clarify this because maybe in the next lab you will be using these low and high directives. So yeah, and remember in the previous lectures, I thought that it was the mistake in the slides, but it was not the actually mistake. It was since the slides are prepared for by focusing on the Arduino IDE, and in Arduino they use low 8 and high 8 instead of saying LOW and HIGH. Okay, yeah, let me simply delete. I can keep this, right? Okay. Okay, so here is a question. How now we can calculate the delay generated by the timer? Remember last time what we talked about in the like previous question, we talked about, okay, I want to generate a delay of let's say 15 machine cycles. What value I should place in the initial value I should place in the register, right? Now we are asking the reverse question. You have a value with which the register is initialized, and then you run the program, and then based on that initial value, you find out what will be the duration of the delay that will be generated, right? So what you can to find the delay generated, what you can do is that you need to first calculate how long is a clock cycle. So one single clock cycle is simply its duration is 1 hour f, where f is the frequency of your clock, right? So if your clock frequency is, let's say, 10 megahertz, so t is equal to 1 over 10. So it will be 0.1 microsecond, right? Now, the second thing you need to do is that you calculate how many clock cycle it waits. So it depends upon the values. So for example, if you had then a value of 0xf1, just like in this example, so if after 15 machine cycles, actually after 15 machine cycle, there will be an overflow, right? So it will wait for 15 machine cycle before the overflow happens. Then the delay will be equal to your time period times number of the clock cycles for which you waited before the overflow happened, right? So it will be, in this case, like t times 15. Okay, so let's say now we want to calculate in this example that what the delay will be generated, and we are assuming that the clock frequency is 10 megahertz, right? So how you can do this is, first thing you need to calculate the time period t, so which is 1 hour f, 1 by 10 is equal to 0.1 microsecond. Second thing is you need to calculate number of machine cycles that will be for which you will wait before the overflow happens. So if you have initial value of, if you put initial value of what was this, 0xf1, so what will happen is that after 15 machine cycle there will be overflow, so the total delay will be 15 times 0.1 microsecond is equal to 1.5 microsecond. Okay, so this will be the total delay. However, this is little bit inaccurate in the sense that we are basically only talk here calculating the delay, uh, like how many machine cycles will be passed uh, before your timer actually results in overflow, right? But in our program, we are also doing something else where we are starting the timer. We are actually starting the timer here at this time point. In this instruction here, the timer is starting, right? And where is the overflow happening? So when the overflow happens, we reach at this point, right? So but in our program we have also uh, some other instructions, right? So in other instructions mean we are first putting initial data in these registers like TC and T0 and control register A. So these instructions also will take some time, right? And similarly, these instructions will also some time for the execution, right? So it is not a correct measurement of the delay. So here we are actually, if we focus only on the timer, how many machine cycles it will take for the timer to expire to overflow. So it's mean that uh, if we have the scare clock, so we will have for 1.5 microsecond, we will have high value on the output, and then for 1.5 microsecond, we will have the low value. But that is not 100% correct. Why? Because you are toggling the value at this point, right? So, and then you are going back uh, to our jump begin. So it's mean that you are not counting for the delay incurred by the execution of this set of instructions and incurred by the execution of this set of instruction, right? So if you want to be like super correct, what you need to do is that you need to also take into consideration the time taken for the execution of the other instructions. So what we need to do is like, remember this is your loop, right? So we know, if we know that each of these instructions they take one cycles, right? One cycle for execution. This SBIS instruction, it will when this is when it will be not set. So it all depends upon your like the branch is taken or not, right? So the branch is uh, if the branch is taken, so you it will take Like branch is taken mean like you are going back here when the flag is not set. So it will take 2 cycles. If the branch is not taken, it will and it falls through, then it will take 1 clock cycle. So how we can calculate the total delay? So this rotation just actually mean that we will keep monitoring the flag. So we need to take into consideration not only the delay caused by the timer, which we have already calculated 1.5 microsecond, but also the delay because of these instructions and these instructions, right? So you can do the math and you will find that actually it is equal to 14. So if like we know how many cycles are taken by each instruction, you can simply sum them. And since each cycle is 0.1 microsecond, when you multiply, you will get 1.4 microsecond. Then the total delay will be basically, so the so total delay before you toggle the output will be not equal to 1.5 microsecond, but it will be equal to 2.9. This will be 2.9 microsecond, and this will be also 2.9 microsecond, right? So the total period of the wave will be 2.9 plus 2.9, which will be 5.8 microsecond. So this will be the clock, this will be the period of the output waves, a scale wave, which we are generating, right? And how you can find the frequency? By simply dividing 1 by the time period. So 1 divided by 5.8 will give you the frequency of 5.8 microsecond, will give you the frequency of 172 kilohertz. So we are actually generating on PB5 a scale wave of 172 kilohertz frequency. Any questions? Okay, so then let's do the quiz. Quiz 4. Okay, you have 60 seconds. So you need to consider the delay only because of the timer. You need to calculate only delay due to the timer, not due to the instructions. Other instructions, just ignore them. Okay, so I don't remember the exact answer, but I think I specified it in the quiz. So, but more important than that is the procedure to know how you can find the answer. So in the poll, okay, I closed the poll. What was the value? Then what was the value we were putting in the initial value we were putting in the register? Let me check. 0x3, right? So you can, what you can do is first that you can convert 0x3 into the hexadecimal into the decimal form if you want, right? So if you convert into the decimal form, it will be equal to 3 into 16, right? Plus 14, right? So you can do the math, or let me do it correctly, quickly on my calculator. 3 times 16 plus 14, 62, right? And Then you can subtract uh, 62 from 256, right? So when you do the subtraction, you will get the value of, let me do it, 256 minus 62, 194, right? So it will take 194 cycles before your uh, overflow happen and the flag will be set. And what is the clock frequency? Was it specified or not? It is specified. It is 8 megahertz. So 1 over 8, 1 divided by 8 is 0.125 microseconds. So when I multiplied 1 with 194, so I get 24.25 microseconds. So the half period will be 24.25 microseconds, and the full period of the one period of the clock will be, you can simply multiply it with 2 of the wave will be 48.5. Okay, so that will be the like how you can find the delay. Any questions? Okay. uh, yeah, so the question is like, how can we initialize the timer registers? uh, so remember that uh, okay. Uh, we are actually already we have discussed it, but here is the like more organized way of saying the same thing which we have seen earlier. So if you want to know that what values you need to put in the register, so first you need to calculate the period of the clock source. So how you can find the period? Period is equal to 1 by frequency, right? So if like for example, if the frequency is 8 megahertz, the period will be 1 over 8 megahertz, right? Now remember last time we said that we wanted to generate a delay of 5 machine cycles or 15 machine cycles. So instead of saying that like we want to generate a delay of 15 machine cycle, if I say okay, I want to I want to generate a delay of 10 milliseconds, right? And then the question is what the value I should put in the register. So this is how we can find that value which is supposed to be in the register initially, right? So first we need to know the frequency of the clock. So if let's say if the frequency is 8 megahertz, we first find the period. So by dividing 1 with the frequency, right? Then what you need to do is that you need the desired time delay. For example, let's say in our case, I'm just writing some, actually there is an example, so I don't need to assume anything. So you divide the desired time delay by the clock period. So for example, if your desired time delay is 3 microsecond, so you divide 3 microsecond with 1 over 8. So when you will do the math, you will find that n will be equal to 24, right? And then you subtract n from 256. So when you will subtract 256 n from 256, you will get a value. So you actually need to initialize your timer register with that value, with the result. You need to initialize with the result of 256 minus n. Is everything clear? Okay, so let's do the next quiz then. Okay, you have 60 seconds. I can give you 30 more seconds. Okay, so uh, I again don't remember the answer, but I specified the correct answers there. Let us do it together here. So what you first need to do is you need to find the time period of from the given frequency. So the given frequency is 1 hour is 10 megahertz. So time period will be 1 over 10, which will be equal to 0.1 microseconds, right? 0.5 microseconds. And then other thing you need to next do is you need to divide your desired time delay with the time period. So desired time delay is what? 6.25 microsecond. So if I do the division, let me do it correctly quickly. So 6.25 divided by 0.1. So it gives me the value of n equal to 62.5, right? So now I can subtract 62.5 from 256. So if I do that, then I'd get the value of 193.5. And you can round it either to 193 or 194. So that's why there were two correct answers, 193 and 194. Okay. Okay. Uh, let's have a look at another coding example. Uh, so assume that you have a crystal of 10 megahertz, so which is like your AVR microcontroller is operating at 10 megahertz. So you need to write a program to generate a scale wave, right, with a period of 10 microsecond on pin port B3. So which basically means that on port B3 we want to have an output of this shape, right? Like an infinite output, and like the high cycle is the high output is 10 microsecond. Oh, sorry, with the period of 10 microsecond basically mean, let me erase it. So the period of 10 microseconds basically means that you have this length is 10 microsecond, right? So if this length is 10 microsecond, then you have high value for 5 microsecond, and then you have a value of low on the output for next 5 microseconds, right? So the delay you want to generate is of 5 microsecond, and then you want to have an overflow after every 5 microsecond, right? So it's mean that now you first need to calculate what the value that you are supposed to put in the register. So how you can do that? So first you need to find the time period. So if your frequency is 10 megahertz, so then time period is equal to 10 microseconds. So which and after that, what you need to do is that what is your required delay before you toggle the output? It is 5 microsecond. Sorry. Time period is not so that the time period of the clock of your wave is 10 microsecond. But what is the time period of your clock, which is on which your microcontroller is running? It is 1 over 10 megahertz, right? So it is equal to 0.1 microsecond. 0.1 microsecond, right? And the delay for which you need to wait before toggling the output is 5 microseconds. So 5 microsecond divided by 0.1 microsecond, you will get 50 clock cycles, right? So you need to wait for 50 clock cycles before toggling. So what value you need to put in the register? Simply 256 minus 50, which is 206. So you need to put the 206 in the TCNT0 register, right? And everything else is the same, almost same as in the previous example, right? So we are putting here 08 in R16. Why we are doing that? Because we will be writing this on the port B, right? So remember we want output on the port B pin 3. So if so 08 is 0, 0, 0, and 1, right? So that's why we will first start this on the output. So on the PB3 we will have the output of 1 initially. So we are configuring the PB3 as output pin. We are loading the value of 0 in R17, and we are first writing R17 on the port B. So yes, we will have the value of low output here, and then we are putting in the register the value which we have calculated 206, right? And after loading TCNT0 with that value, we are selecting the normal mode of operation for the timer by writing the control register A, and in by writing the value of 1 in the control register B, we are starting the timer. And then here we are now uh, waiting. We are actually polling, or we are monitoring the flag bit of TIFR0 register. Remember that in this example, coding style is little bit different. Actually, it makes the program longer as compared to the example which we have seen in the previous slides. Like if I take you back, uh, here, here what we were doing, we are using the SBIS instruction, right? So we can directly monitor we are monitoring the 0th bit of the TIFR0 register. Uh, in this second example, we are not using SBIS instruction. What we are doing is that we are saying, okay, read the TIFR0 register in the R20 register, and then use SBRS instruction. What is this SBR instruction? It is actually just like SBIS instruction. What is SBIS instruction? It means skip if the IO bit is set, and SBRS is skip if the register bit is set, right? So we are saying look at the 0th bit of R20 register, and if it is set, then skip this next instruction, this RJump, right? But remember, what is R20? R20 is copied from, like, it has the copied value of TIFR0. So effectively, it is the TIFR0. So if the 0th bit is set for the R20, we will skip the next instruction, which means if the flag is set, we will skip the next instruction. If not, we will go back to the again label, which means we will be again monitoring, we will again check the flag. And we will keep doing as long as the bit is not set, the flag is not. And once it is set, the control will continue to the next instruction. In next instruction, what we are doing here, we are stopping the timer. Again, this code is like little bit lengthy. I don't know why this example is written this way, because these registers are in a standard IO address space, so we can actually use SBI and CBI instructions between with them. But here we are first putting the value of 0 in the R20 register, and then writing R20 in the control register B, so which will actually put 0 in the 0th bit of the register, and which will effectively stop the timer, right? Then we need to clear the flag. So for that, we are saying, okay, shift 1 to the left for 0 time, and put the value in the R20, and then write R20 in the TIFR0 register, right? So it will actually write 1 in the 0th bit of the TIFR0, right? Which will clear the overflow flag. And then everything else is same. We are doing exclusive OR between R17 and R16, and we are 17 and 16, and we are setting the value of the result to the port B, which will now make the output high. And then we are saying, okay, go back and do the same thing again. Any questions? Okay. Here, what we want to do is to modify the TCNT0 in example 2, in the previous example, to get the largest time delay possible with no prescaler. So prescaler is what? Before, let me tell you what first prescaler is, and then we will go back to the example. Where is that figure? Yeah, here. Remember that output of this mux is connected with the clock input of the register, right? So if the faster the clock is, it's mean that the value of the register, it will increment quickly, right? But if the clock is slower, then it means that the value will increment after a longer delay, right? So for example, let's say I am putting the value of only 254, right? So let's say if my clock is faster, so it's mean my time period is smaller, so my positive edge becomes arrives earlier. So let's say my clock is faster, so the positive edge arrives after every, let me make some simple numbers, after every 1 microsecond, right? So after how many microseconds this will change, the overflow will happen? So 254 to 255, 1 microsecond, right? So if clock period is 1 microsecond, and then from 255 to 256, right? So which is equal to 0, right? So only two clocks, right? So I need two clocks. And the what will be the total time? 2 times 1 microsecond. So 2 microseconds, right? Now, let's say I use a slower clock. I use a clock which is like uh, 10 times slower, right? So if it is 10 times slower, it's mean its time period is 10 microseconds, right? So if it's mean that one positive edge arrives after every 10 microseconds. So initially 255 is 54 to 255, it take one clock cycle, then 255 to 256, it takes one more clock. So two clock cycles in total, what I will have, 2 times 20, 20 microseconds. So it's mean that if I use the slower clock, even with the same register value, initial value, it will take longer time for the overflow to happen, depending upon the clock frequency. So how can I generate longer delays? One way is that I keep the register value same, but I make the clock frequency lower, slower clock. So if the clock is slower, it will take longer time. The other option is that I keep the clock frequency same, but I put the initial value of the register, I reduce the initial value to 0. So like if I reduce it to 0, then it will take the maximum number of clocks to reach it to the overflow point, right? So that is prescaler. Like prescaler is mean what frequency you are selecting here. So if you are selecting this one here, original frequency, it's mean you are using no prescaler. The same clock frequency which is uh, applied to the all other components of the AVR microcontroller, same clock frequency is also applied to the timer. But you have the options like you can have a prescaler of clock by 8, where the clock frequency is 8 times slower as compared to the frequency applied to the other components, 60 times slower, 256 times slower, and 1025 times slower. Now let's go back to the example. So yeah, so now we need to modify the example to such that we can get the largest time delay possible with no prescaler, which basically mean we use the same frequency as applied to the AVR microcontroller, and we need to find the delay in microsecond. And your calculation do not include the overhead due to the instructions. So we are interested in finding the our delay, uh, maximum delay generated only by putting the value in the timer register. So what we can do is like in TC and T0, we can put the minimum value. So we are putting 0 in R20, and then we are writing R20 to TC and T0. Everything else is same. So now it will take much longer time to for the overflow to happen, right? So how can you find the delay? We know the frequency. So frequency is 10 megahertz. So time period will be 0.1 microsecond. How many clock cycles will take will consume before you actually have the overflow? 256. 256 times 0.1, you will have 25.6 microsecond. So this will be the delay before the overflow will happen. We have 5 minutes, right? What is the other option? What are the other options available for creating the larger delays? One thing is that you can count a short time period many times, right? Uh, before uh, you can say like, okay, I will flip the output or toggle the output when the overflow happens 2 times. Like what we have done in the previous example, that as soon as the overflow happen, we toggle the output. This time we say, okay, no, I will count and see when, wait until the two overflows happen and then toggle the output. Or you can say, okay, I will wait for 10 overflows to happen and then toggle the output. So now you are generating longer delays before you toggle the output, right? The other thing is that you can use the prescaler as I just explained earlier. So if you change the clock frequency, if you slower the clock, it will take longer time because now it will count slowly. Because now that input, the register value will change with slowly as compared to the faster clock. And the other thing is that you can use the bigger counters. The bigger counters mean like now we are using timer 0, which has only 8 bits, so it can count from, so the overflow happens when your value change reaches 256, right? So if you use, let's say, 16 bit register, so the overflow will happen when your value will, the minimum value if you put 0, and the maximum value will be what, 2 raised to power 16. So when your value will reach 2 raised to power 16, then overflow will happen. So it will take much longer time for the overflow to appear. So this is what they meant by prescaler, and so this is the same figure which we have seen earlier. So here, when you select 0, it's mean no clock. So it's like the signal is only low, a low signal is provided on the input, so your timer doesn't work. It doesn't count anything. 1, 2, and 3, 4, and 5. These are clocks. So one is original clock, and 2, 3, 4 are slowed down versions of the original clock, and with different scaling down factors. And 6 and 7, here what you are doing saying is that T0 is actually a pin on your microcontroller. So whatever signal or sensor you connect with the T0, you are saying I will use the external input to uh, to control the clock of the register, right? So if it is like you select 6 or 7, so if you select 7, so whatever you value have coming from the sensor will be used to control incrementing the counter. And if you just use 6, the complemented version of the input will be used. So if the on the 0, if you have input 0, then output here will be 1, and then there will be a positive edge. But if you have input 0, input 1, the output here will be 0, and then there will be negative edge. Okay. uh Let me check the time. Yeah, today you have quiz, right? And we have 2 minutes. I don't want to start the new subtopic, which is another mode of the timer operation, clear timer on on compare match, so a CTC mode. So we will talk about this mode in the next lecture. So let's stop here for now. Do you have any questions before we go to the quiz? No questions? Okay, so if no questions, then that's it for now. I am available online uh, until end of the